Hello, let's discuss some basics of combinatorics in today's video. Coming to what is mod, it is just the remainder when a is divided by b. So 10 mod 3 is equal to 1 because 3 into 3 plus 1 is equal to 10. So the remainder when 10 is divided by 3 is just this one. And similarly 12 modulo 2 is 0 because it is directly divisible by 2 and there is no remainder, so it is 0. So a mod b is the remainder and the value can go up to 0 and mod minus 1. And coming to why this is used in competitive programming, the maximum long value that we can store in integer is 2 power 63 minus 1, which is approximately 918. And in terms of factorial, it is between 20 factorial and 21 factorial, which are significantly less. And what if our answer is greater than this? And for example, if our answer to some question is 2 power 120, and how can we return this to the function as the maximum number is this? So we use mod so that we can always return some long value even though our answer exceeds the maximum value of integers. So this is called overflow, and that's why we will use mod. So we will return answer modulo mod to answer to specify this. And generally mod is prime. This is used because to reduce the collisions, because a mod b is always 0 to mod minus 1. So for different years the values are always between these. So to reduce the collisions we will use mod as prime. And coming to some basic observations by using mod, a plus b whole mod m is equal to a mod m plus b mod m plus whole mod m. So 2 mod 3 is equal to 2 and 7 mod 3 is equal to 1, and this is 3 and the whole mod 3 is 0, so it is 0. And coming to minus, a minus b whole mod b is equal to a minus b a mod b minus b mod m plus m whole mod m. Why this m? Because for example here a mod m minus b mod m is equal to minus 1, so just minus 1 mod 3 is same as adding m because m mod m is 0, so we can add 3 here so that the whole value will become positive, and now it is generally the remainder. So minus 1 plus 3 2, whole mod 3 is 2. And similarly the multiplication, a mod m into b mod m whole mod m, it is 2 here. And coming to division, 7 by 2 whole mod 3, let's discuss this after. So now coming to the power, so what if we want to find a power b modulo m? So the first idea is we can just try to loop for all the values of b, and we can just multiply answer with e. So as we are doing this b times and we are multiplying for b times, answer will be a power b. But the time complexity of this is O of b because there is a loop of b. But what if b can go up to 1e9 and 1e10? So we cannot just multiply b times so that we want a power. So this is not the efficient one we use generally. The next one is, it is called binary exponentiation. For example, if the value we want is 2 power 10, and if we try to observe, it can be written as 2 power 5 into 2 power 5 because it is 2 power 5 whole square. And if it is 2 power 11, we can write it as 2 into 2 power 5 into 2 power 5. So if we observe this carefully, for a power b, we want a power b by 2 value. So if we get this based on b, if b is even, it is a power b by 2 whole square. And if b is equal to odd, it is a into a power b by 2 whole square. So a power b requires only a power b by 2, and a power b by 2 requires only a power b by 4 similarly, and so on. Finally a power 1, so b by some 2 power k. So the base case is we can return a if b is equal to 1, as a power 1 is equal to 1. So the iterations are up to this. So initially we are finding from a power b and we are finally from to a power 1, and the power is gradually decreasing in terms of power 2. So the time complexity of this is O power log b because it is 1 initially, 1 by 2 and 1 by 2 square and so on. So lastly it is 1 by 2 power k, b by 2 power k, so it is 1. So k is equal to log b to the base 2. So if we do by this way, the time complexity is log b, which is very significantly less than this. And even for values like 1e9 and 1e10, the number of iterations are approximately 31. So we are able to perform this in approximately constant time. So in this way we can try to optimize the a power b. And coming to next one, and now coming to the initial question, what is 7 divided by 2 whole mod 3? So this is not directly like 7 mod 3 divided by 2 mod 3, because this should be always be an integer and should lie between 0 to 2. So if we are trying to do 7 modulo 3 by 2 modulo 3, it will not be an integer and it's wrong. So how can we write this? So it is simply 7 into 2 power minus 1, because it is into 1 by 2 and it is 2 power minus 1 whole mod 3. So it is simply the multiplication. 7 mod 3 it is equal to 1, and 2 inverse mod 3 and whole mod 3, as we discussed in the model multiplication. And now coming to this, what is a power a minus 1 whole modem? This is inverse of a to the modem. By Fermat theorem, if m is a prime, we can write a inverse modem is equal to a power m minus 2 modem. So based on this theorem, if m is prime, as here 3 is a prime, we can write this as 2 power 2 whole mod 3. So it is 1 in this case. It is 2, because m minus 2 is 1 and it is 2 power 1 mod 3. So 2 inverse whole mod 3 is 2. So from this theorem we can find the even division as well in terms of a power b itself. As we have discussed a power b here, similarly in the way for a inverse we can find a power m minus 2 in O of log m time. So coming to next one, and let's discuss the last one of today's one. So it is a factorial. So what is factorial? For example, if there are 5 integers 1 to 5 and there are 5 boxes, and what are the number of ways to fill all these so that we can fill all these. So coming to first one, we can keep a 1 or 2 or 3 or 4 or 5 here, because there are, because all the numbers are available and this is the first one. So the total cases to keep any number is 5. We can put 1 or 2 or 3 or 4 or 5. So for example, if we assume that we have used 1 here, so the remaining cases are 2, 3, 4, 5. So there are 4 cases to keep any number here, 2 or 3 or 4 or 5. And if we try to use 2 here, other 3 numbers are left, and the cases here are 3, the possibilities, and similarly 2 and similarly 1. So because these are independent, the answer is multiplication of these. So the total number of ways to fill 5 numbers in these 5 boxes is 5 into 4 into 3 into 2 into 1, and this is 5 factorial. So a factorial is a into a minus 1 and so on, and it is generally the number of ways to keep given numbers in given number of box. So now if we want to find a factorial mod b is equal to a into a minus 1 and so on up to 1. So we can do modular multiplication similarly, and we can get in O of a for a given a. But what if there are many values of a and we have to find factorial of all? For example, the first one we want is 10 factorial, and next we want 9 factorial again, and then we want 10 again, and so on. So we cannot do this for all a. So what if we can try to pre-compute all? For example, we can take the maximum value we want initially. For example, the values are 10, 9, 10, 1, and 11. If we want the factorials of these 5 values, we try to find the maximum value of this. And if we just try to find the factorial for this, we want the answer for 1 if I minus 1, and that one answer for 1 if I minus 2 and so on. And that requires 11 factorial, and we want 10, and then we want 9, and so on up to 1, and then we can reach the base case. So if we can try to pre-compute, we can get all answers in of 1. So for a we want a minus 1, a minus 2 and so on. So we can pre-compute them and we can get in of 1. So let's check the code. For example, the modulus value is 1 in n plus 7. This is a prime, and the maximum value is 1 if I. Let's assume that this is the maximum value and this is 1 if I. And we are trying to find the power of a power b by binary exponentiation. So the base case is if b is 0, it is equal to a power 0, which is 1. So return 1. And now we want a power b by 2. So int x is equal to a power b by 2. And x is equal to x into x mod m, because we want 2 power 5 into 2 power 5 in both even and odd cases. So we can just replace 2 power a by 2 power 5 into 2 power 5, because we want in this both cases. but we multiply with an extra a if it is odd. So x is equal to x square, and next if b mod 2 is 0, so if it is even, return x because it is just the value of x, 2 power 5 and 2 power 5. And if this is even, if this is odd, we will reach this and we can return a mod x, a multiplied by x mod m. So this is a power b by 2, and the time complexity of this is O of log b, which is generally constant. And now coming to the inverse. So we discussed that a inverse mod m is equal to a power mod my 2 mod minus 2 whole mod m. So it is power of a mod minus 2. By this we can get inverse of a. Similarly in O of log n time. And now coming to factorial. The base case is 0 factorial is 1. So factorial of 0 is 1. As we discussed that we have to pre-compute the factorial values, we can use a vector which stores all the values from factorial of 0 to factorial of 105, and we can just use a loop, and factorial of j is equal to j into factorial of j minus 1, and we can traverse whole the loop and we can get all values of factorials from 1 to mx. So before using the factorial in the code, we can just try to run this function so that the values of fact will be filled in this array, and we can use this in next part of the code. Drop a like and comment below. See you in the next one.